Welcome everyone. My name is Niels van Hoorn at NVH on Twitter. I work at a company here in Amsterdam called Framer, who built a design tool. And apart from that, I organize a conference called Swift Island. Swift Island is a conference happening on an actual island on Texel in the Netherlands. And to explain what it is, I created this nice infographic. So you all know the excitement coming up to WWDC, right? Like this is WWDC, so you got really excited, and then WWDC starts, and that's a lot of fun. And then after WWDC, you start watching the videos, and then your confusion starts, right? So what we created Swift Island to mitigate that. So during Swift Island, we will give workshops on the topics being presented at WWDC. Which makes your confusion go down, and then your excitement goes back up, and it's even more fun than WWDC. So if you want to attend, ticket sales aren't live yet, but they will be very soon. And if you use the code CocoaHeadsNL, you get a €40 discount. So that's really nice. But that's not what I'm here for. I want to tell you a bit why I created this talk, because I have a master in artificial intelligence. But whenever I talk to engineers about machine learning, I get the feeling that they find it hard to understand what's going on. And I have an assumption about this, which is because we're used to give computers instructions through code, when you tell an engineer that a system can train itself, they get confused, right? Because like, how can a system train itself? And it kind of feels like magic, while it's just another algorithm. So today, what I'm going to try to do is reveal the tricks. Oh, hello. Be the magician that reveals the trick, like this guy. And I'm going to explain that it's not magic that actually runs neural networks, but it's math. I had a lot of fun with Keynote today. So there's actually three pretty simple mathematical functions that you need to understand. And even if you don't understand them, you can understand the algorithm that uses them to build a neural network. So bear with me. This is going to be a little bit of math, but if you fall asleep, I'll wake you up later. A sigmoid is a function which I will show to you later, which we use inside of a neural network as an activation function. And what this function does is basically you can pass it any value, and it will transform it to a value between 0 and 1. And I'll explain to you later why this is important. Then we have the derivative of a sigmoid, which is a pretty simple function. Which is basically, a derivative. And if you're not good at math, it doesn't matter. Then we have the third function, which is the root mean squared error, which does exactly what it says. So it takes a bunch of error, like a list of x's, then it squares them, these twos here, and then it takes the mean, so it sums them and divides them by the number of elements, and then it takes the root. And this is useful to actually see how far off, like to create one number out of a list out of errors. We'll use these three functions throughout my live coding talk. So the second inspiration for this talk was a guy named Richard Feynman. I don't know if you know him. You see him here in front of his blackboard. And he was a brilliant lecturer and a physicist. And one thing that he wrote on a blackboard is, what I cannot create, I do not understand. And we're going to take that quote by heart and build a neural network from scratch. So that hopefully in the end you will understand it better. So what exactly are we going to build? It's a machine learning solution, which is called a neural network. And it consists of a network of neurons. And each neuron is modeled after the biological neurons that are in your brain and your body. So a biological neuron has multiple synapses that fire into the cell of that neuron. And when the potential gets high enough in that cell, then it fires through its axon. So a artificial neuron is modeled after this. So it's not exactly this, but it uses that as a model. So what it does, it takes like a number of inputs, like with the actual neuron. It multiplies them by some weights, then it sums it up, and then it goes through an activation function. And then it has one output. So these are pretty much the only similarities between a biological neuron and an artificial neural network. So it's just the inspiration that is taken from biology, not a specific replication of it. So a little bit of warning. We're going to implement this, but yeah, don't try this at home. The code that I'm going to write is just for training purposes, I guess. It's probably highly inefficient, and like there are much smarter people than I that have actually created libraries that do the same stuff. This is just for understanding things, so I would suggest using those. So, live coding is a lot of fun, but I am not a robot. So if you're like, I think I spot a bug, or you find yourself making this face, just raise your sword or your hand or whatever you have at hand, and we'll fix it together. And if you're like Neo in the Matrix and you're like, what? Or you're like the Fresh Prince and you're like, what? Or I go full The Shining and you're like, no! Just tell me and I'll try to explain it a little bit better. So let's get started. I'm going to do this in Swift Playgrounds on my iPad. And here we have two of the three functions I talked about, and I'm just want to show them to you. So first is the sigmoid, which is, as I said, a function that will, so let me show it to you here. Which is a function that will take its input. Here we loop over -10 to 10, and we pass it to the sigmoid function, and then it converts it to a value between 0 and 1. We can see that here. And actually, it doesn't matter if I take like 100 and 200 here, and I run it again. Then like the value will be really small, but close to 0. And the maximum value that we get out will be actually 1. And the graph of that still looks a bit like this, only a little bit squished. So I'm going to use this function in a bit, and then you might understand a bit more why this is useful. And then we have the derivative of this sigmoid, which is actually using that sigmoid function. And it's basically like it describes the steepness of the curve, right? So here the curve is pretty steep, so these values are high, and then it's flattening out, so the values start too low. And we're going to use this basically as a reverse of the sigmoid function. So that's basically what you need to know. Like we have a function, it goes from anything to 0 to 1, and then we have the kind of reverse, the mathematical reverse of that function. What are we going to model? It is going to be, at first, just some logical functions. So I have a NOT function, an OR function, an AND function, and XOR function. To show what they do, I have here, like if I do not true, it is false, and I can change this. So I can change this to false, and then it will return, hopefully, come on, true, yes. And then I have this OR function here. Which is 3 values, false, false, true, and that is true, obviously. But then if I change this one into false, it becomes false. There we go. And then I have a AND function. Come on. This, which is now false because this value is false. But if I change that to true, it will become true too. And then the XOR function, which you might be the least familiar with, which is actually a function that is only true if both values are different. So in this case, it is true because true and false are different. But if I change true to, if I change this false to true, it becomes false. And then if both are false, it's false again. And then if this one is true, basically these are the 4 options, right? So what we are going to do with these functions, where are they? Here, is we're going to train these functions with a neural network. So basically to show you how a simple neural network can train, we will use these functions. So let's remove all this stuff, and then we can get started for real. So I'm going to start with a bunch of protocols. And the first protocol is called predicting. And in this protocol is a function that predicts. For that, it needs a bunch of inputs, which is an array of doubles. And then it returns one double. Sorry. And then we have a different protocol. Do we have a piece of paper or something like that? Sorry about that. Nope. Yes. Yeah, much better. So, where was I? Yes, a protocol called learning, which is actually derived from predicting, so it will also contain the predict function. And we have a function called learn, and we're going to tell it basically, okay, what you did before, this is the error on that, and I want you to learn with a specific speed. So, let's create something that adheres to these protocols, which is called a neuron, like I said before. So this neuron has a bunch of inputs, which is a list of double, and it has a bunch of weights. And the weights are basically how much the input adheres to the output of the, or influences the output of the neuron. So let's create an initializer that we pass the number of inputs, and then we create self.inputs inputs equals a array which will be repeating just 0 because this is the initial value for the number of inputs, and then self.weights will be an array which will be repeating a double.random in a space of -1 to 1, and it will also be for num inputs. So now we have a bunch of inputs, a bunch of weights, and we need an output. So we're going to create a computed variable, which is a double, and that contains a sum, which is a double, which is 0, and then for each input, for index in the inputs, dot enumerated, because we need the index too, we're going to add to the sum, come on, yes, add to the sum the input times the weight that corresponds to that input. Weight with the specific index of that input. Oh, what's happening? Yeah, here. So, weights, thank you. Yes. It looked funny to me, but I couldn't tell what was it. So now we're going to use one of these functions, which is the sigmoid. So let's stop a bit and see what's happening here. So I'm creating a sum of basically whatever you pass me, which can be any value. I'm multiplying it by some random value that I initialized between -1 and 1, but it can, I'm going to change them later while learning. So it can change to anything. So this sum can become basically any value between -infinity to +infinity. So this is why we need this sigmoid function. There are other functions that you can use for this, but we are going to use the sigmoid function to basically squish this sum into a nice value between 0 and 1. So it's good to know that the output always has a value between 0 and 1. So now we can actually implement the protocol predicting. And what do we need to implement for that? We need to implement a predict function. Well, this is pretty easy because we can just set self.inputs.toInputs, and then we can just return the output, which will use those inputs. So that's easy enough. You might want to ask, why don't you don't use those inputs, and why do we need to store them inside of this neuron? This is useful because later we want to also use the output, so we need to keep track of what the input you just passed during the learning process, that is. So now we're going to change this neuron to learning. And for that we need to implement a learn function. So a learn function is passed an error and the speed at which we are learning. And we're going to create a error term, which is the error that gets passed times the derived sigmoid of the output. So here, because the output uses the inputs that from this neuron, it is nice that we stored them previously. So now we're going to update every weight. So index weight in, this is going to be inputs. In inputs dot enumerated, and we're going to we're going to add to the weight the initial input that was given to this neuron times the error term that we just calculated times the speed that we want to learn at. So the speed is basically the let's move this up a bit so you can read it better. So this is weights index. So the speed is basically the rate at which the network adjusts itself. So basically you can, like if you set the speed to 1, then you basically say I want the input to really quickly move to the value that I expected as an output. If you set the speed low, the weights will update slowly and converge to what we have. So this is basically everything it takes to build a neuron. So let's see it in action. So I'm going to create a variable called num_inputs. And this is going to be 1 at first. And then we're going to create a learner, which is the neuron. And it has the num_inputs. So now for to train this, we're going to create another function called teach, and we're going to teach the learner, which is a learning, conforming to the learning protocol, and we're going to teach it some examples, which is a type example. So this type example, let me enumerate over that array, example in examples. And an example basically contains the inputs that you expect and then the expected output. So basically we create a bunch of examples with these inputs should match to these outputs, and then we're going to teach that to the learner. So how are we going to do that? Well, we're first going to ask the learner, like, okay, if I pass you this input, predict what the output will be. But at this point, it probably doesn't know anything, but we'll see. So we're going to take the inputs from the example, and then we're going to calculate the error, which is basically what the example.expected, so basically what we expected from this example, and then we're going to we're going to subtract the actual output that we gotten from that. So this expected variable, I hope it shows now. No. Wait one moment. So a neuron has just one output, which is a double, but we're going to create a network later. So this expected value is actually an array of doubles, of which we only use one. So for now, we're just going to get the index 0 of the expected array. And then we have an error, so we can tell the learner, well, what you just did, you had this error on that, and I want you to learn with a speed of 0.3. These are variables that you can tweak, obviously. Oh, I've forgotten something, which is this learner now has some weights assigned to it, right? So let's look at those weights a bit. So now it has, it has one weight, but if I add more inputs, it has more weights. But as you see here, the weights of this neuron are all the same because this array repeating function, it just takes, like it calculates the double random, it takes it one time, and then it creates an array out of it. So I actually created a handy function which is behind the scenes, which will actually put an auto closure around this argument and then call that multiple times. So it will actually create different values. You will see me using this function a bunch more times. Now it actually creates different values. So where were we? We were with the teacher, the teach function. So the teach function basically let the learner predict something, then calculate the error, and then let the learner learn from its error. So now we have this list of examples, so we need to get that from somewhere. Well, luckily I've created a function before. That is called create examples. And this function, I pass one of my Boolean functions, so and or not. In this case, I'm going to use not, and I'm going to set the inputs to 1, and I'm going to pass it num inputs. So what this does, it creates basically a bunch of examples for my network to train on. So in this case, I want to model the not function. And for the inputs, I modeled 1 as true and -1 as false. And then for the output, I already said like the output's always going to be between 0 and 1. So I modeled true or false as 0 and true as 1. So true becomes false and false becomes true. So these are the examples that we're going to learn. So now let's look at, for example, the AND function and create examples for that, but then let's use a little bit more inputs. So now it's going to basically create an array with every possible value for true or false. So this is true becomes true, and then true false becomes false. Well, you get it, probably. And then if I do the OR function, it's the same. So now I can use these examples to teach my network. So we're going to start with not. And then, so I'm going to teach my network, teach the neuron, or what's it, the learner. I'm going to teach it the examples. And now I'm going to see how well my network did. So I'm going to iterate over all the examples again and see what example in examples, and see what it predicts for every example. So my learner, I'm going to see what it predicts for example dot inputs. And it's a value between 0 and 1. So if it's larger than 1, I'm going to call it true. And then I'm going to get the example dot expected and see if that is larger than 0.5. And again, for the example, the expected is an array. So now let's see what it did. So here it created true. Wait, let's make this a list. So here it created false true and false true. So this is correct. But now let's run this again. And then at some point, there we go. So now it actually, like I taught it something, but it actually doesn't predict the correct value. And this is because I'm only giving it one set of examples and saying like, okay, this and this, learn this, right? But neural networks need a lot of data and need a bunch of training. So what we basically need is to have this inside of a loop and teach it the same examples over and over again. So what I'm going to do now is do this 100 times. And then you'll see that every time I run it, it will actually always be the correct value. So now I taught my single neuron, I taught it a not function. Let's see if we can do the AND function too. Or the OR function. Wait, OR, yes. So let's do it with 2 inputs because otherwise it doesn't make a lot of sense. And here you see like, hey, I'm teaching it 100 times, but it doesn't actually have the correct values, right? Because it's supposed to be true, 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 false, but here we have a wrong value between them. And this is actually because like I'm initializing this network with all random weights. And then I'm starting adjusting these weights like also a bit randomly, right? And this is just too much randomness basically for the neuron to handle. So what it needs is basically a stable factor where it can say, okay, this is always the same, so I can adjust my inputs based on that. So in machine learning, this is called a bias. And a bias is basically an input that is always 1. So you feed it, it's a similar input as the other things, but and it also has a weight, but you basically always feed it 1. So it is some stable factor in the network. So to the initializer, I'm going to add a add bias argument, which is a bool which I call true by default. Then I'm going to store that bool. And then we need a number of weights, which is the number of inputs that we have here. But then if we have a bias, we're going to add something to that, because we need one extra weight, right? So if we have a bias, then we're going to add 1, otherwise we're going to add 0, and then the number of weights go in here. And then every time, and then we need to save the add bias as well. And every time we are predicting, we are going to add this extra input to the array of inputs. So I'm going to append 0 or append 1 here. So we basically, like from the inputs you get predicted, I only also add a 1, and then the latest weight in the list is applied to that one. So now if I run it, you'll see that every time it comes up with the correct values. Oops. So now I can also teach it, the OR function, or I taught it the OR function. Let's teach it the AND function. Oops. So something's going wrong here. Let's see. Segment hour term. I lost the prediction here. So self.inputs.append.1. So now it can also teach the AND function. But what about the XOR function? So the XOR function is a special one because it isn't a linear function, because for some values it's false, and then it becomes true, and then it becomes false again. And this is actually a function that is not possible to learn by a single neuron. So we need a network for that. So let's create a network. So the network is going to be a class again, class network. And this network is going to have a number of hidden, it has a hidden layer, which is a list of neurons. And it's going to have an output layer, which is also a list of neurons. So let's initialize this with a number of inputs again, inputs, which is a number of hidden neurons, which is a int, and a number of outputs, which is also int. And then I'm going to initialize the hidden layer with the repeating function that I created with a neuron, with num hidden. Yes, with a neuron that has the number of inputs that I have. So you might want to ask, like, hey, why don't you store the inputs here? But like, because the hidden layer has a input for every input in my network, this is the list of inputs. And then I'm going to do the same for the output layer. Oh, sorry. Come on, hello. Yes. The output layer is fully connected to the hidden layer. So the number of inputs from the output layer is actually the number of hidden neurons that I have. So I here need the num hidden, and then the output layer contains as many neurons as I specify in num outputs. So now I'm going to make this one predicting 2. But first I'm going to change the predicting function a bit. So where I used to return just one double, I'm now going to return an array of doubles because I have a list of outputs in my network now. And this error is also becoming, like every output has a specific error. So let's implement that. Like I have some errors in below now, but we'll fix them later. So the predict function gets the inputs, and what I'm going to do is get the hidden values out of that, and that works by getting the hidden layer and mapping that with the predict function of every neuron that I already built. So I'm mapping that to the inputs that I receive, and then I get the output values in a similar way. But then for the outputs layer, and I map them with the with the predict, and what I pass in here is the hidden values. So we're basically propagating the values through the network here. So I first pass the inputs to every neuron in the hidden layer. That gives me a value for every neuron in the hidden layer, and then I pass those values to every neuron in the output layer, and then that gives me the output values that I can then return. So now we need to change a bit here because, first we're going to make this learning too. So that needs we need to implement the learn function. And the learn function is basically going backwards. So we have some output from the network. We have a list of errors that we expected from the output. And then the learn function, like in artificial neural network terminology, it's called backpropagate, but I think that's a weird term, but it's backpropagating the values through the network. So I think learn is a more, how do you say that? Specific name for it. So we're going to iterate over all the outputs in the output layer, and then we're going to, for every output, we're going to learn dot enumerated. We're going to learn from the error that we have been given, which corresponds to this output layer with the speed that we tell it to. So then we need to get those values and learn the hidden layer. So we're going to do the same for that. So we iterate over the hidden layer. We're going to get the error that we expected from that we expect at this point. And for that, we basically need to calculate what the value or the error would have been if we multiply it by the weights of the output layer. So let's code this up, and then I'll explain it a little bit more. So the hidden error is a double. Double, yes. That starts at 0, and then for output index outputs in output layer dot enumerated. We're going to add to that all the errors from the output index. So we're going to get the error that corresponds to this output neuron, which is the output index. And then we're going to multiply it by the output dot weights. And then the weight that corresponds to this hidden neuron, which is this index. But as you might have noticed, like at this point, we already updated the weights. So if we start using them here, then we don't really, it won't really work well. So what we need to do in the neuron is we need to keep track of the previous set of weights. So is what we're going to do. And then we are going to set self.previous weights equals weights. Then just before we start adjusting the weights in the learn function, we are going to store the previous weights that we had. So now here we can use the previous weights, and then we'll be all fine. So what's error? I have errors here. So let's. So now we can learn the hidden neuron. We can learn it, the error that we just computed, the hidden error, and then with the same speed, hidden error. And that's basically it. So this is like a network that can train, I can show you the XOR function, but first we need to calculate the list of errors based on the outputs that I've gotten. I've gotten a handy struct for that, which is a mistake. Not an actual mistake, but a struct called mistake. And what you can pass this is basically the thing you expected. So that is coming from the example. Example. And then the actual, which is the output. And then I've created a mistake.error. Did I create that? Yes, it's here. So it's an extension on mistakes that will basically take every expected value and subtract from it the actual value and then create a list of errors from this. So here I can say mistake.errors and pass that into the learner. Example.expected. And now the learner needs to become a network that we created. So it's a network with num inputs, with 3 hidden layers and only 1 output. We are going to use more outputs later on. And then if we predict, we're going to need to take the first output there as well. So now it's going to learn 100 times and we'll see if it worked. And here you see that the values are actually learned correctly. So the only thing that we did is used a bunch of math and then created an algorithm that we could feed a bunch of data and then it will learn the function that we pass it. But as you might see, at some point, if I keep rerunning this, at some point the output that I expected, it is correct for most of the time, but isn't correct. This is because we initialize it with all random weights, and sometimes it isn't able to optimize it in just 100 steps. And sometimes it's able to optimize it even quicker. So being dumb and saying hey, we just wanna have this 100 steps is actually might not be the smartest thing to do. We want to repeat this until the network is basically not learning anymore. Well, we can do that by returning a list of mistakes from the teach function. So we're going to keep track of that here. Mistakes is a list of mistakes. And then we're going to add the mistakes to mistakes.append to the list of mistakes. So with this list, we can later on check if the network has actually stopped learning. So I'll show you in a bit. Mistakes. So now we can keep track of this mistake. So mistakes is a list of mistakes, which we're going to initialize with 0. And then we're going to set mistakes to teach. And what we're going to do now is we're going to repeat this while we're not finished. And we're going to pass that the mistakes. So let's implement this is finished function.
Type is called mistake.
Yes, thank you very much. And then here, yes. Cool. Yes, so we don't have is finished yet. So let's implement that. So we're going to pass it a list of mistakes, and it's going to return a bool to say if we're finished or not. So what we're going to do now is get all the errors from the mistake. Did I do something wrong here? I don't think so. Let me just check if I can get this to compile or we have an error somewhere else.
Initialize the var mistake.
Yes, thank you. Yes, so now we're going again. So we're going to get the errors from the mistake. So we're going to map the mistakes and then get all the errors map. And then get all the errors from it. But this errors is actually a list of errors. So for every output we have an error. So first we're going to sum this. So this is actually a helper function that I created earlier. Now from these errors we are going to use this third math function that I show you, which is a root mean squared error. And we are going to call that the mean. And what we could do now is basically say, okay, if the mean of the errors goes below something, then I want to stop, right? But first of all, you don't really know when, like I know because I did this before. So it's around like 0.5 where you can see that it will, like if you see here, like the mean goes down a lot, and then at some point it will stop. But as you see here, like the way it learns, because it initializes randomly, can be very different. So basically what we want to do is not say, okay, I want a mean below something, but I want to calculate like the difference, and when the mean doesn't adjust anymore, then I want to stop. So the difference will be the previous mean minus the mean. And then I want the difference to be lower than, I think it's this value. This is a bit of magic here. So let's keep track of this previous mean. And then return false. And so we need to store these falso. It's not Italian. This is going to be, the previous mean is going to be an optional double. And then here we need to store the previous mean also. So now we can look at this function, and this is actually really interesting because we can watch the network learn, right? This is pretty cool. So here we see the mean, so the errors basically going down. And here we see the difference, so like how fast we are learning. And then if this value at some point goes below like this 0.0001, then we know that the network isn't changing and updating the means anymore, so we can stop. So that has happened now. And now we can show this list. And you'll see that the things actually updated to the right values. So this is basically showing a simple neural network with a simple algorithm with fixed data, right? But now for my final trick, I'm going to use a different setup, which is going to discard basically all of, well, not all of it. Oh, it's still computing? No. Yes. So I don't need any examples. I don't need this. I just need a network with 3 inputs, 3 hidden layers, and 2 outputs. So what I did as preparation, I created a special view that I will now initialize and assign to the playground page, current live view, and will be the view. And this is actually a camera view. And what this basically does, let me align this a little bit more. Come on. What this basically does is it will detect rectangles using a CI detector. And then inside of those rectangles, it will take the center, which will be the images that you see on top of there. So, well, let me set this to teach. It will actually take the center image, and from that center image, it will take the pixel and get the color from that. So as you see here, I have a black and a red card, and it will actually, like the squares are black and red there. So now we get a color that we can feed into our neural network. So let's do that. On this view, there is a function called should_learn. And this function actually has the following signature. It has a color for the left card and a color for the right card. And then we can basically feed that into our neural network. So I also create some helper function, which is UI_color.components. So .red, for example, .components. And this will actually, let me remove this. This will actually convert a color into three inputs that we can feed into our neural network. So if I take blue, for example, the third one will be highlighted. And then if I take, oh, hello? So if I take, name another color, gray. Is that a color? Probably. Then you'll see that everything is 0.5. So these are the values that we can put into our neural network. And then I've created like basically a enum, which is called label, which has three values, which are unknown, red, and black. And on top of these functions, I've created a output, which is basically the output I expect. So for red, or for black, this output is the first one will be 0, and the second one will be 1. And for red, the output, this output will be 1 and 0. And for unknown, they're all both 0, but we are not going to use that in this occasion. So now we can implement the should_learn function with this. So we have a left color and a right color, which are both UI colors. And then we're going to create two examples. Example 1, which is an example, which has inputs left color dot components, which is the helper function I just showed. And the left card is black, so we are going to, the expected values is going to be label dot black dot outputs. And then the other example is pretty similar, but it is an example for red. So this one will be red, and we're going to take the right color for this. Oh, right color. And then example 1 and example 2. So now we create a list of examples that we can feed into the teach function. So first example 1 and then example 2. And then our learner, which is our network, can, we're going to use the teach function, teach. We're going to learn our learner these two examples. And we're going to do that while, if we're not finished, so this will return the mistakes, just like we had earlier. And if we are finished, what we're going to dispatch async on the main thread, because this is all happening on a background thread, the view.stop learning. So what that will basically do is like tell the view to not pass the function and call the should_learn function. So then I need to show you that this actually works. So we have a should_predict function as well. And what this function gets is just one color, which is the center color of the card it will have detected. So it will get a color. And with this, we're going to pass that just to the learner, which is our network. And we can predict the color.components. And then I need to dispatch on the main queue again. And then I can set this output on, output on the view. And I've created some helper functions that will actually show you the output in a nice way. Oh, outputs is actually a better name for this. Okay, so let's run this. And let's first set this up. So here, if I start teaching, you'll see that here, the data that's being passed is much more noisy, right? But we'll see here that the mean is going down, and it now actually, like, the difference became low enough, like it saw that it isn't learning anymore. So now we can actually predict and like look at this card, and it says, hey, it's black. And we can look at this card, and it says, hey, it's red. So I can do this basically with these cards now too. So this one is red, and this one is black. So this is all being used by, or being done by an algorithm that we just implemented in, what is it? Well, an hour. It is, it's only feeding it just data from the camera and telling it, like, this is the thing. So what we can do, last trick, is not teach it about, like, it doesn't know that what red is and black is, right? Not teach it about red and black, but about blue and red. So this has a little bit less chance of succeeding, but it sometimes does. So now I taught it that actually blue is black. So let's see if it will work. Yeah, so it will flash a bit of black, and then red is red. So this is a little bit more noisy, but it's nice because I could have created an algorithm that just detect like blackish colors and reddish colors. But now we can actually feed it like any data, and it will learn from this data the example, like it will learn from the examples that we have provided. So that was it. Thank you so much for sticking with me. Are there any questions? Or just anyway, everyone just want to grab a beer? Yes.
I was hoping you would point the camera at the water bottle.
Sorry?
I was hoping you would point the camera
at the water bottle. Yeah, well, yeah, I can do, but this won't. Like, oh, to detect blue, you mean? Oh, yeah, sure. We can try. Let's see if we can teach it. So, teach.
How do I say dop in English?
Dop? Cap.
Bottle cap.
Bottle cap. So, what I need to do now is like, because it detects rectangles and takes the center of that. So I need to basically do it like this, and then, yeah, it has a. So I can teach it like this color blue, because it's kind of different, right? So, and then check if it will, I don't know. No, so it's pretty specific on what the thing is it learned. So let's try this over a beer and then get it to work. So another question.
At one point you said XOR can be learned by just one neuron.
Sorry? XOR, yes.
Can be learned by just one neuron.
Yes.
I have learned this at some point, but I forgot.
Yes.
So why is that?
So the only thing a neuron can learn is something like the output of a neuron, as we said, and I've repeated a couple of times, is, I don't have it here anymore, so 4i in minus 10 to 10, let x equals double I, sigmoid x. So the output of a neuron always has this shape, right? And at one point we are going to map this to a Boolean, right? So this will be false, and this will be true. And XOR is shaped not like such a function, but basically in the beginning it will be false, then it becomes true, and then it becomes false again. And because the output is always mapped with such a function, you can't actually express that kind of function with a single neuron. And that's why you need like a collection of neurons so that they can interact together, and then with multiple of these outputs you can come up with a value that is actually that. Make sense? Any more questions? Yes?
Serious one. I was wondering, you mentioned the speed.
Yes, the learning rate, yes.
How do we determine the speed? What does it mean?
Yeah, well, so you saw the, during the learning, you saw the difference going a bit up and down, right? So if you increase the learning speed, the network will adjust like quicker to the examples you give it, but it will also forget quicker the examples you shown it earlier. Right? And for the fixed examples with the Boolean function, that doesn't really matter because the examples are always the same, right? But if you feed it like real data, then the learning speed actually like fits best to the data it just saw. And then if you only want to adjust it a little bit based on the new data, it will like you decrease the learning speed. Does that make sense?
Yes, but how do you determine it?
Oh yeah, just by trying. It is, yeah, this is like, neural networks are these things that can do, like, they can fit any function, but to do that, like how many neurons you need to put in your network, what your learning rate will be, like all these things you just need to, like, they are specific to your problem set, so you will just like have to try what learns quickest. So, cool. I guess that's it. Hey, let's grab a beer.